This will be an Algebra 2 screencast where we cover the zero product property. We're going to state it and define it. We're going to discuss the three forms of the quadratic and how they are helpful to us in Algebra 2. We're going to talk about how to apply the zero product property to the factored form and what we get from it. And this will be our opportunity to kind of marry these two ideas that we talk about first. And finally, I'll give you an example on how to utilize the zero product property in finding roots, and I will define roots for you. I just wanted to take a moment to note here that this is a unit that explores quadratics and other polynomial functions like third degree, fourth degree, fifth degree, and higher degree polynomials. And this screencast is setting you up to understand some things about quadratics that we will later be able to apply to higher degree polynomials. So this is kind of one of the foundation screencasts. So let's start with the zero product property. The zero product property says that if you have two numbers that multiply to give you 0, and actually this property also applies to multiple numbers of variables that multiply to give you 0, then either x must be 0 or y must be 0, or both variables are 0. So like let's say you have x times y times 4 equals 0. We have three things that multiply to give you 0, and the only way you can get a product of 0 is if either this or both numbers equal 0, because obviously this will not equal 0. And like I said, you can apply this to several variables. Like if I have three things that multiply to give you 0, then one, more, or all three have to be 0. That is a zero product property. So moving on to the three forms of the quadratic, the first form is the general form, which we see here. Examples of general form include these three polynomials or quadratics. These are second degree polynomials that form quadratics. And often, like we saw today in class, we can find this general form from a data set. It shows us the y-intercept of the parabola and the leading coefficient. So what I mean by that is the y-intercept is where x equals 0, right? So on a graph, an xy graph, two-dimensional graph, wherever I have my function, the y-intercept is where x equals 0. So you can easily see that if you plug in x equals 0 here and x equals 0 here, you're just left with the y-intercept, which is always going to be this constant. I also state that you have a leading coefficient here, and if you can remember back from a previous chapter, the leading coefficient tells us the vertical dilation of our parabola, so whether or not it's kind of skinny or a little bit wider. So that would be two benefits to the general form, not to mention that this is often what we can find from a data set. The next form is vertex form. Again, another form you're quite familiar with, because in a previous chapter we learned that this form of the quadratic is commonly known as the graphing form. There should be another little quotation marks there. And this tells us what the vertex of the parabola is, and the vertex would be hk. So just to give you a quick review, if I have a parabola, the vertex is the lowest point on the parabola. So let's say this is your parabola. Then here the vertex would be the highest point on the parabola. And that point is the point hk. And if you have your equation of your parabola in this form, then you can easily see the vertex right there. And again, we have our leading coefficient, which we learned was the vertical dilation. So this will be a form that is nice because it's the graphing form of your parabola. It helps us graph it. And here are three examples of vertex form for you. So can check those out. Notice that this one doesn't have a number here, it's just 0. So this would have a vertex of 3, 0. And finally, the third form of the quadratic, which is the one we're going to be most interested in as we move further into higher degree polynomials, is called the factored form. So we had general form, vertex form, and this is factored form. It's factored form because you can see the factors of the quadratic, and I have added on a leading coefficient here because oftentimes you can actually factor out a common divisor. So like an example of that would be if I have y equals 2x squared plus 14x plus 7, then, oh, 7's a bad example, sorry. Let's try 8. Then you can see that each of these terms has a factor of 2. So you can factor out a 2, like undistribute it, and you'd be left with this. Then, if you could get this into a factored form, you might have something that looks like this. Here are 3 examples of factored forms. 2 with leading coefficients, 1 without, just has a 1 there. And as you can see, you know, you can have coefficients on the inside. It's just we're going to start without them. So, why the R1 and the R2? So we can find, let me erase this here. The reason the factored form is nice is because it allows us to find roots of our parabola. Roots are the x-intercepts of the parabola. I have a couple of illustrations here to show you what roots are. So here we have an upside down parabola. Here would be the x-axis and the y-axis. And the roots occur here and here. And notice that this is where y equals 0. You could also have just one root where the parabola comes down and just barely touches it in one, well, it just touches it at one spot and then goes back up or goes back down. So here your vertex is your only root. Roots of a parabola are x-intercepts on the graph, and these are also called zeros. This is always, always where y equals 0. So, where y equals 0, how can I apply that back to the factored form, like I said I wanted to, and start utilizing the zero product property? So here we have an example of a factored form of a quadratic. And we will review in class how to get this form and how to factor. Now, if I'm trying to find the roots, so again, the roots are the x-intercepts. These occur when y equals 0. So you can see here I've substituted in a 0 for y. Now, the zero product property says either 4 has to equal 0 because I have a multiplication problem here. 4 times 2x plus 3 times x minus 4. So either 4 equals 0, or 2x plus 3 equals 0, or at some point x minus 4 equals 0. Now, obviously this is ridiculous, right? I'm kind of just proving a point here, that it can't be that. Like our 4 is not the 0. So one of these guys has to be 0. And here's where you would just simply solve for x. So I'm going to subtract 3 from both sides. I can ignore the parentheses, since there's not a number there. Then I'll divide by 2, and I get that x equaling 3/2, this, if I plugged it into this equation, would give me a 0. And so that is the x value on the first root I have found, and that is negative 1.5. So if that's negative 2, then I have a first root right there. Over here, if I solve for x, I can easily see that x must equal 4. So that is my second root. So 1, 2, 3, 4. And I'm calling them roots, but again, they're just x-intercepts. So those are the x-intercepts of my parabola. Now, if I was asked to sketch this parabola, I would see that it has a vertical dilation of 4. And if you recall, a number greater than 1 causes the parabola to be quite skinnier than the average parabola. So it looks like, I'm not exactly sure where the vertex is, but I know that this guy is going to be somewhat skinny, and it's going to have x-intercepts. I kind of messed that up. It's going to have x-intercepts at those two x values. Wow, I cannot draw with this thing. Okay, well, the point is that there are your roots, smiley face, and they occur at x equals 4 and x equals negative 3/2. And that is how the zero product property applies to the factored form of a quadratic.